In the last video, we talked about the graphs of various equations. And to get more familiar with how these graphs can go, it's helpful to have kind of a library of known curves. In fact, we've already kind of started to do that. Recall when we looked at quadratics, something that looks like, say, y equals ax squared plus bx plus c, we notice that we always get what we call a parabola. Specifically, if we look at kind of our standard parabola, y equals x squared, we get this U-shaped curve that hits the origin there. And any other quadratic is really just the same curve, but moved around and or rescaled in some fashion. So we already have an idea of what these kind of curves can look like. And if we can recognize that our equation is a quadratic, then we can actually use the information that we already have to get an idea of what it should look like. If we plot points on the on a if we have our equation and we plot some points based off that equation, then we can use the fact that we already have an idea what the shape looks like to make sure that we do have the correct curve. In fact, I think it only takes like 4 points on a parabola to be sure of exactly what parabola it is. But we have to know it's a parabola before we can use that. Actually, it should be 3 points on a parabola. Yeah, 3 points on a parabola tells us exactly what parabola we're talking about, as long as we know it's a parabola in the first place. Another simple category are linear equations. These can be something that looks like maybe ax plus by is equal to c. As long as not both a and b are equal to 0, this is going to be the equation of a line. Now you might be more familiar with the form of y equals mx plus b. This doesn't actually capture every line. There are lines where, say, b equals 0 and we can't solve for y. But the point here is any equation that has one of these two forms is, when we graph that equation, it becomes a line. We'll talk more about finding lines and determining what these different variables, MB, ABC, what all that means in the next section. We'll be talking a lot more about lines in the future, but we want to just kind of throw this in here. We have our standard model here of y equals x. That's kind of well, it's not the simplest line, but it is the simplest one where it's not too simple, I guess. This is a line that passes the origin, and it makes a 45-degree angle with both of the two axes. We could also look at the lines, say y equals 0. That's actually going to be a little hard to draw in here. Maybe I'll use a color just to be clear. That is the y-axis. You remember, any point on the x-axis. Any point on the x-axis has a y value of 0. If we have, say, x equals 0, and this one we can't use the y equals mx plus b format, but we can use the ax plus by equals c format. If we plot this one, then we have the y-axis, because this time we can't have any distance along the x in the x direction. We can only have along the y direction. And so we have various different lines or linear equations, and we get an idea of how these things can behave based off of the fact that we know that these from the format of the equation what we have. If we didn't know we had a line and we just plugged in some values, we'd have a bunch of points along here, but we wouldn't ever be entirely sure that we did have a straight line. But once we can recognize the format, once we can recognize the structure of our equation, then we can get more information from that structure. Another model here, this is getting a little bit more complicated, is the cubic. This would be something like y equals ax cubed. So here we're going beyond the square that we had for quadratics. But we can have any power of x less than 3. Of course, we have our standard model here of y equals x cubed. Well, I should state here that we don't want a to equal 0. If a equals 0, then all we have is a quadratic. And so we don't need this more complicated category. So here a is not equal to 0. But if a equals 1 and everything else is 0, then we have our kind of our standard example. I'm just going to go ahead and graph this. Actually, let me make this a little bit clearer. It does really level off there, but then it keeps going up. It does not turn around like like quadratics do. This is our standard cubic. Unfortunately, in general, cubics can actually deviate more from their shape than quadratics can vary from their standard parabola. And that's true if we raise the power on x more and more. The higher the power of x we allow, the more freedom the curve has to take more non-standard forms. But we have various possibilities. So something like y equals x cubed minus 1. This one actually goes above the x-axis, but then comes back down and hits still at the origin, and then actually turns back around and goes up to infinity. On the other hand, we have something like y equals x cubed plus 1. This one, it looks a little more similar to the y equals x cubed, but instead of flattening off at the origin, it just kind of keeps going up. This one actually really does become completely horizontal at the origin before continuing on. This one does not flatten out quite as much. And it turns out any cubic is going to look similar to one of these three forms. The differences in the A, B, C, and D's will just mean, well, this can be moved around, and it can be stretched, and all that kind of stuff. But whether or not it's one of these particular forms is something you have to actually work a little bit to actually figure out. And calculus can actually make that a lot easier for us than we could if we just have algebra. Next example, we're going to look at the square root. Note, I should remind you here, because this is actually going to be pretty useful to remember in calculus. Remember, the square root is actually a power of x. It is x to the 1/2 power. The point here is if I square the square root, I'm supposed to get the x back. And if I square the 1 to the 1/2 power, then that square just multiplies this 1/2 by a 2 and gives us a 1. If we want to plot this thing, we can actually use stuff that we've already developed. If we square both sides of this, we can turn this into the equation that y squared is equal to x. And this looks very similar to our standard parabola, except the x's and y's have been switched. So if I were to basically plot our parabola, but swap which axis is which, then we can just graph a parabola on its side. Not my best looking parabola, but you might get the idea here. We have a parabola on its side. The problem here is that this is not a graph of our square root function, because when we take the square root of anything, we assume by default that we are taking the positive square root. Therefore, there should not be any negative y's, because all the y's should come as square roots of some x. This definitely has negative y values down here. So we need to exclude all that part. We need to get rid of this part of it. So really, our square root function looks more like this, where this looks a little bit better than what I drew over here. This is y equals square root of x. There's not a lot more to say about that here. You just have to be careful about little tricks like this. This does give us some information. This is part of a parabola. It really is the same shape as a parabola, but we just have to be careful about what parts of the parabola we include. Let's move on to another one. We're going to look at the absolute value. Now, you might not remember exactly what the absolute value does, but the absolute value takes in a number and gives us the positive part of the number. So things like the absolute value of 2, because 2 is already positive, it gives you 2. But if we put in, say, negative 3, since negative 3 is negative, we have to get rid of that negative, and we're just left with the positive 3. Now, it turns out we can actually write this in a piecewise fashion. That's what we call it when we get to split up our equation into multiple pieces. When x is a positive number, or non-negative number, we'll include 0 here, then all we have to do is just return what number we had. So when we plugged in 2, we got 2 back. When we plug in a negative number, when x is less than 0, we could actually put less than or equal to 0 because we'll get the same result either way. But we want to change that negative number into a positive number. And so we'll write this as negative x. But really the negative here is getting rid of a negative that's already there. So we'll actually end up with a positive. But the important thing here is that if you look at the different pieces of this, we have y equals x and we have y equals negative x. And which one we actually use just depends on which side of the y-axis we're on. So if we're on the right side of our plane, then we're following the formula of y equals x. And remember, y equals x just looks like a line. It is a line. But we just only have part of it because we're not using the same formula on the other side of the y-axis. On the other side of the y-axis, we're using y equals negative x. That is still a linear equation. It's still a line, but it's a different line. In fact, it's the line that comes in this direction. And so we actually get this V shape. And it's our first example of one that's not perfectly smooth. We have a very sharp corner here at the origin. And this will be an example that we'll come back to when we look at derivatives, because that sharp corner actually turns into a problem. And it's a nice example of when we run into those kind of problems, that's not too complicated. But for the moment, that's all we're going to talk about with the absolute value. Our next example, we're going to look at the equation y equals 1 over x. Or we can actually rewrite this as xy is equal to 1 if we move the x to the other side. These are actually the same equation. We don't have to worry about any change in what actually ends up on our graph. Now this is actually an interesting example because we can't actually draw this as a single curve. Instead, we actually have two pieces to it. We have one piece that's over here, and that should be a little more vertical there. Another piece that's over here. And there's actually no way to connect these two pieces. And we can tell that from the fact that we cannot plug in 0 for x or for y, because if we plug 0 into either one of those, we get 0 here. We don't get 1. So this curve, this graph, cannot have any x or y intercepts. And so we get this particular shape. We cannot touch either of the axes. The axes become what we call asymptotes. And we'll talk more about what those mean as we move forward. We'll be talking about those in. Might even be talking about those at the end of this particular chapter. But we'll definitely talk about them at some point. Basically, this curve does approach the axes. It gets really, really close to the axes. It never actually touches them. If you want a name for this curve, it does actually have a name. This is actually an example of a hyperbola. So similar to the parabola, this is a standardized shape. Though the fact that this is a hyperbola is maybe a little not obvious if you get into various shapes of different equations that become hyperbolas. Just kind of take my word for it. We also can sometimes start with some geometry and get a particular equation from that. Let's talk about circles. Recall that a circle is a set of points that are some fixed distance from a fixed point. So if we have our fixed point that we call the center, we'll give this the coordinates HK. And we're talking about all points that are the same distance from the center. That fixed distance is what we call the radius. We'll go ahead and use a little r for that. So if a point xy is on this circle, then the distance between xy and hk has to be r. That's our definition for what that circle means. Well, we can use the distance formula. Basically, if we look at the distance between xy and hk, we have the square root of this difference between our x values, that's x and h squared. The difference between our y values is y and k squared. And we want that to equal r. Now here, r has to be some positive number. We definitely can't have any negative come out from the square root. And if we set equal to 0, then really we're just working with the center itself. It's not really a curve, it's just a point. So we'll assume that here we have a positive radius, and so by their distance formula, we have that this distance is equal to r. Now, we'd like to not have to deal with the square root if we can help it, so we'll go ahead and square both sides. There's actually no problem there because everything ends up being positive. We already had r is equal to a positive number, and everything underneath the square root is already positive because of the squares. And so this is our general formula for a circle. X minus h squared plus y minus k squared is equal to r squared. So let's go ahead and plot a particular one. Just kind of off the top of my head, let's take a center of 3, 2. We have a point here. Let's even go ahead and rename this. We'll call this center. That's going to be the center of our circle. Now we want to look at the circle around the center with a radius of, say, we can go out to 5. And so we want x minus the x value of our center. So in this particular case, the 3 here is the h. We'll square that. GeoGebra is trying to plot what I have here already. If I set y equals x minus 3 squared, it actually is a parabola. Then I need to put y minus my y value. My y value is a 2. That's the k from our equation from before. I'm going to square that as well. And now, because I chose a radius of 5, I need to put 5 squared. Or I could go ahead and write in 25, because that's what 5 squared is. But the point here is, I have my circle. This is a circle around that center with a radius of 5. So just, let's say we go out horizontally from the point 3,2. We end up over here at the point 8,2. That's a distance of 5 away from the center. Now, we do have a particular one that we like to talk about. It's called the unit circle. This is where we have the center is the origin, just 0, 0, and the radius is equal to 1. And so by our formula, so h and k are both 0, we just have x squared plus y squared over here. And then we have the radius 1 squared. So x squared plus y squared equals 1. This is a very common equation that you can work with a lot. Now, in this particular course, we'll probably not see it as often as you might in a regular calculus course, because circles actually have a lot to do with trigonometry. There's actually a lot that we can't really work with on circles unless we have that trigonometry to back us up. In fact, trigonometry actually kind of, even though the name trigonometry seems to have something to do with triangles, and it really does, a lot of times those functions are referred to as the circular functions, and trigonometry frequently starts with an investigation into the unit circle. But that's getting a little off topic here. The point here is that this is an example of another graph, another curve that we can work with in terms of algebra. And that's really what we're looking at here. We're trying to find a way to relate the geometry of curves to the algebra of equations. And sometimes this is referred to as algebraic geometry. Alright, I'm going to go ahead and leave it there. Just trying to get some idea of what kind of curves that we have, how they relate to the different equations we can come across. Of course, later on in the semester, we'll have even more tools to actually connect the equations with the curves more easily, and know that we do have the correct curves to the particular equation that we might be started with, or vice versa. But for the moment, that's all we're going to talk about. So I'll see you guys in the next section.